Today, we are tackling one of the most famous, maybe infamous, charts in all of science, the periodic table. You've seen it hanging in just about every science classroom, right? But what is it really? Well, let me tell you, it's so much more than just a poster. It's the ultimate cheat sheet for the entire universe. So, let's get into it and unlock its secrets.
But first, let's start with the huge question. Imagine I could give you a box that had one of every single type of atom that exists. You know, all the basic building blocks of matter. How in the world would you even start to organize that? It's a pretty mind-boggling task when you think about it.
Well, for hundreds of years, that was the exact puzzle that scientists were trying to solve. They kept discovering new elements, things like gold, oxygen, carbon, but it was all just a jumbled mess, a completely chaotic collection of cosmic ingredients with no rhyme or reason. What they desperately needed was a system. They needed a map.
So here's our roadmap for today's journey. We're going to start with that early quest to crack the elemental code. Then we'll decode the modern table's layout, get a handle on the rules that make it so powerful, and finally, really dig into why this chart is one of the most important tools science has ever created.
Okay, so our story really begins with this incredible quest for order. You see, scientists knew there had to be patterns hidden among the elements. They could feel it. But finding the secret logic behind it all, that was a puzzle that took the better part of a century to finally figure out.
So, in the early 1800s, a guy named Johann Dobereiner noticed that some elements seemed to hang out in groups of three, or triads. Then, fast forward to 1865, and John Newland saw that properties seemed to repeat every eighth element, kind of like notes in a musical scale. But the real breakthrough, the one everyone remembers, came from Dmitri Mendeleev. He arranged the elements by their atomic mass, but his stroke of genius was leaving blank spaces, gaps for elements that hadn't even been discovered yet, and he even predicted what they'd be like.
Mendeleev's table was an absolute game-changer, no doubt. But there were a few spots where it didn't quite work. And that's because all these early attempts were built on a foundation that was just slightly off. They were all organizing the elements by their weight, their atomic mass. They were so close, but they were missing the one true key.
And this is it. This is the pivot that changed everything. The monumental shift was from organizing by atomic mass, basically how heavy an atom is, to organizing by atomic number, which is just the number of protons in its core. That single change made everything snap into perfect, beautiful alignment. And that's how we got the modern periodic table we know and love today.
All right, so let's start decoding this thing. Honestly, the best way to think about the periodic table is like a giant city map for all the elements. Every single element has its own specific address, and that address tells you pretty much everything you need to know about it.
The vertical columns, the up and down ones, are called groups or sometimes families. Think of them like streets in our city. And just like houses on the same street might all be bungalows, all the elements in the same group have similar chemical personalities. Why? Because they have the same arrangement of electrons on their outer shell. It's why everything in group 1 is super reactive. And everything in group 18, the noble gases, are, well, they're perfectly content to just keep to themselves.
Now, the horizontal rows are called periods. As you move from left to right along one of these rows, you're adding exactly one proton to each element. So their atomic number goes up by 1, 1, 1. And as you do that, the properties change in this really cool, predictable, repeating pattern. It's where the name periodic table comes from.
And if you take a step back and look at the whole city, you'll see one thing right away. It is dominated by metals. I mean, look at that. They make up over 3/4 of all the known elements. The nonmetals, they're all kind of huddled up in the top right corner. And sitting right on the border between them are the metalloids, which, you guessed it, have properties of both.
To stretch our city map analogy just a little bit further, the table is also broken down into 4 main neighborhoods, or blocks. They have these simple letter names S, P, D, and F. Now, this all has to do with some pretty detailed electron physics, but for now, just think of it as another way the city is zoned, another layer of organization that helps chemists navigate the landscape.
Okay, now we get to the table's real superpower. This is what makes it so incredible. It's not just a chart for organizing stuff. It's a predictive tool. The rules of the row, and the columns too, let us predict how an element is going to behave just by seeing where it lives.
Yeah, an element's address on this map is anything but random. It literally tells you its secrets, how big its atoms are, how it's going to react with its neighbors, all of it. And these predictable patterns that we can see all across the table, we call those periodic trends.
Let's break down some of the biggest trends. Look at atomic size. Here's a weird one. As you go from left to right across a period, the atoms actually get smaller. Seems counterintuitive, right?
but it's because the nucleus is getting stronger and pulling the electrons in tighter. Then, as you go down a group, you're adding whole new layers of electrons, so of course they get bigger. And metallic character? It decreases as you go across, but increases as you go down. It's these simple rules that tell us so much.
And what about reactivity? This is one of my favorites. The most reactive, most energetic elements live on the absolute edges of the table, the far left and the far right. The elements in the middle, they tend to be a lot more stable and less reactive. And those noble gases, all the way over in group 18, they're the most chill, unreactive elements of all.
So why are we spending all this time on a chart from chemistry class? Why does it matter so much? Because understanding this map, it means understanding the fundamental building blocks of absolutely everything, from the device you're watching this on to the most distant stars in the sky.
So if you take away just a few things today, make it these. First, the table's magic comes from organizing everything by that simple atomic number. Second, an element's location isn't just a location, it's a cheat sheet to its properties and behavior. That makes it the ultimate ingredient list for the entire universe. It's a master key that unlocks doors in chemistry, physics, and even biology.
And that leaves us with a final, really cool thought to ponder. Right now, scientists are working to create brand new, super heavy elements that don't exist in nature. So if they announced tomorrow that they had made element 120, think about this. Just by knowing where it would sit on this table, what could we already tell about it? Before running a single experiment, what would we already know about its size, its character, and how it might react? That is the true power of the periodic table.